I'm going to start working through the homework here. So our first question, we have a wave pool in California, and the waves are moving too slow in this wave pool, and so we want to know what we can do to change how fast the waves are moving. And really, the key idea here is the medium must be changed. That's the only way that we can change the velocity of the waves is change the medium. If we want to be a little bit more specific, we could think about what we could change about the water itself. That is the medium in this case, the thing the waves are moving through. So we could potentially change the temperature of the water. We could change maybe the density of it by changing how much salt is in the water. There's lots of different options, but the key idea is you have to change something about the water itself. All right, so for this first question here, we're told that at the shore, waves crash on the beach every 2.3 seconds. And the first question is just what is the period and what is the frequency? Well, the period is that 2.3 seconds because the period is defined as the time between waves. So that is going to be the 2.3 seconds. For the frequency, we can just say that the frequency is 1 divided by the period. So our frequency here is going to be 1 over 2.3, which gives us a frequency of 0.43 hertz. Moving on, we're told that the ocean waves travel at a speed of 3.7 meters per second, and we want to know the wavelength. And so we can use our equation for the velocity of a wave, and that is that velocity is just wavelength times frequency. We're told that velocity is 3.7, so that's going to be equal to our wavelength, which is what we're looking for, times our frequency, the 0.43 that we just solved for. We divide by that, and we find that the wavelength in this case is going to be 8.5 meters. All right, moving on to this next one, we're creating waves on a slinky, and so in order to do that, a person is moving their hand back and forth every 0.45 seconds, and that means that that time there is our period, how long between the creation of waves. And so we first want to find the frequency. Frequency we know is just 1 divided by the period, so that frequency is going to be 1 divided by that 0.45, which gives us a frequency of 2.22 hertz. The next question is we want to know what is the wavelength of our waves here. And so the thing I would immediately jump to here when we're looking for the wavelength is our velocity equals wavelength times frequency equation. We just solved for our frequency was the 2.22, but the problem is we don't actually know what the velocity of our waves is here. However, we do have some information that may be able to help us out, and that is that the wave travels 7 meters down the slinky in 1.9 seconds. So we can think about basically kinematics here. Now, waves travel at a constant speed, they don't accelerate. So we can just set that to be 0. We know our time is 1.9 seconds, and our displacement here is going to be 7 meters. And so we can go ahead and solve for our velocity. And so we can say delta x equals VIT plus 1/2 AT squared. Like we said, that acceleration term goes away. And so you really just get this delta x equals velocity multiplied by time, which is true in cases when something's not accelerating. So 7 is going to be equal to our velocity times our time, which was 1.9 seconds. So we end up getting a velocity for these waves of 3.68 meters per second. So we can then take that and use that velocity, 3.68, to solve for our wavelength. So we divide by the 2.2, and we get that our wavelength here is going to be 1.66 meters. Last question here, we want to know what could be done to change the velocity of these waves. And the key here is we need to change the medium. Once again, that's the only way to change the velocity. So a potential example would be we could change the tension in the slinky. That would be an easy way to change the medium, something about the slinky, what the wave's traveling through, which would ultimately change the velocity. All right, so for this next one, we have a situation where we have Otis Redding watching these waves travel into the bay. The first thing we're told is the distance between wave peaks is 2.4 meters. So that is telling us the wavelength, distance between waves. And then the other piece of information we're given is that 4.5 seconds is how long it takes 4 wave peaks to pass by. And so if it's 4.5 seconds for 4 waves, okay, we can figure out how long it is for one wave, and that's going to be our period. So our period, t, is just going to be 4.5 over 4, which gives us 1.125 seconds. So that is our period. And we ultimately want to know how long it will take these waves to cross the bay. But what I'm going to find first is I'm going to go ahead and find the velocity of my wave here. Okay? And so the way we find velocity of a wave is velocity is wavelength times frequency. We know our wavelength is this 2.4 meters. We can then solve for our frequency using the period that I just found. So frequency is 1 over the period. So 1 over 1.125, and I end up getting a frequency here of 0.89 hertz. So we can substitute that in, 0.89, and then we find that our velocity for these waves is going to be 2.13 meters per second. Using that velocity and some other things we know, we can ultimately find how long it will take. So we needed to travel a displacement of 80 meters. We know that the initial and the final velocity is going to be 2.13 because waves are going to travel at a constant speed, assuming the medium doesn't change. And so we can solve for our time. So I can say displacement is VIT plus 1/2 AT squared. That term goes away. So it's just going to be 80 equals 2.13 multiplied by my time here. And so I end up getting a time of 37.5 seconds. All right, for the problem 5 here, we have 2 different graphs. In each case, you see we're given one additional piece of information plus the graph, and we want to solve for velocity, period, frequency, wavelength, and amplitude. So starting with graph A here, we're told the velocity is 38 meters per second, so I can sub that in for velocity. I'm then going to read the graph and get some information from the graph itself. So for amplitude, that is the distance from equilibrium to a crest or a trough, which in this case is going to be 8 meters. So I can go ahead and record that for my amplitude. I also, if I look at this x-axis, I see that it's in meters. So I can see that one full wave is going to be from there to there. Since the x-axis is meters, this gives me my wavelength. And so my wavelength is going to be 5 meters. And now I can go ahead and do some math. So the first piece of math I'm going to do is velocity is wavelength times frequency. So 38 equals 5f, which means my frequency here is 7.6 hertz. And so I can sub that in for f here. And then the other thing I can do is I can find my period based off of the frequency. Period is just going to be 1 over that frequency is 7.6, and so I end up getting a period here of 0.132 seconds. So I can sub that or plug that in as well, and there I have all of the information for wave A. Moving on to wave B, the key piece of information I'm given here is that my wavelength is 70 meters. Okay, I can get my amplitude here, of course, from going ahead and reading my graph. So from the equilibrium position up to the peak, it's in between 4 and 6. We'll call it 5. That's about what it looks to be there. So that's my amplitude, 5 meters. The other thing I can get is if I look at this graph, I see that the units for the x-axis are going to be in seconds. And so I can read the graph to get my period. So it's going to start here. One full wave would be up to this point here, which is right in between 1 and 1.5. So I'm going to say that my period is 1.25 seconds, halfway in between. So I can sub that in there. And then from there, I can go ahead and calculate my frequency and ultimately my velocity. So to get that frequency here, I can say frequency is 1 over the period So it's going to be 1 over that 1.25. So my frequency is 0.8 hertz. And then from there, I can go ahead and solve for the velocity of the wave. Velocity is just wavelength times frequency. So in this case, it's going to be 70 times 0.8. So I end up getting a velocity here of 56 meters per second. And now I have the second wave analyzed.